So, welcome everybody to the last session for this academic year of the Western Hemisphere Colloquium on Geometry and Physics. We're delighted to have Jacques Distler, who will talk about n equals to superconformal field theories and families of Hitchin systems.
Excellent. Thank you, Ron. So what I'm going to talk about today is some ongoing work. Yes, I know. Some ongoing work with Ashwin Balasubramanian in Bangalore, the aforementioned Ron Donaghy at UPenn, and my student Carlos Perez. Let me start by noting that supersymmetric field theories in general have a moduli space of inequivalent vacua, and the low energy physics, these go by various names: Coulomb branch, the Higgs branch, and the low energy physics on this moduli space of vacua is generally governed by a highly nonlinear effective Lagrangian for the massless degrees of freedom. And it's just shy of 30 years ago that Seiberg and Witten made a great breakthrough in understanding that effective field theory and worked out how to compute the effective field theory for 4D n equals 2 supersymmetric quantum field theories on their Coulomb branch of vacua. The relevant degrees, the salient points about the Coulomb branch is that the gauge group is abelian. The SU2R symmetry of n equals 2 is unbroken. And the geometry of the moduli space of vacua, the field theory metric that governs the long wavelength fluctuations of the scalar fields that parameterize that moduli space of vacua, is special Kähler, not just Kähler as it would be in n equals 1 supersymmetry, but this sort of fancy variant, which has various different definitions, hopefully most of which are familiar to the audience, but if not, I'll refer you to an old paper by Dan, which beautifully reviews the various different definitions and explains how they're related. What will be salient for us today is the fact that a special Kähler space, B, saying that B is special Kähler is equivalent or is encoded in the statement that B is the base of a complex integrable system. And the data of this complex integrable system determines the special Kähler metric on B. Now, when you look either at Seiberg and Witten's original paper or the hundreds of papers that followed it, you find ubiquitously that the complex integrable system that appears is a Hitchin system. And you might ask, why is that? I mean, of all of the complex integrable systems that could appear in this context, why is it that we seem ubiquitously to get Hitchin systems? The answer really was given very beautifully by Davide in 2009 when he pointed out that if you start with the 2-0 superconformal field theory in 6 dimensions, these come in, there's a sort of ADE classification of these guys, and you compactify them on a punctured Riemann surface with a suitable topological twist, you get a 4D n equals 2 theory at low energies. And as explored beautifully by Gayotto, Moore, and Knightsky in a series of papers, the Coulomb branch geometry of that 4D theory is encoded in the Hitchin system on this curve C that you compactified on. And the ubiquity of Hitchin systems in the n equals 2 supersymmetric field theory literature is just the statement that class S theories form a very wide, but perhaps not exhaustive, class of 4D n equals 2 theories. So that's why we keep seeing Hitchin systems over and over again. It's because they came from 6 dimensions. I'm going to specialize to the conformal case today. So in that case, the Higgs field, which was allowed to have poles at marked points on the Riemann surface C, here will restrict the residues of those poles to be nilpotent. And that is what leads to a superconformal theory. This gives us, in this case, the integrable system is symplectic rather than Poisson. And as a assumption, I'm going to assume that the Coulomb branch as a complex variety its coordinate ring is freely generated. There are oddball, this used to be a folk theorem that the 4D Coulomb branches for n equals 2 were always freely generated, but then some oddball counterexamples were found. And towards the end of the talk, I'm going to suggest that perhaps there's a much wider range of counterexamples to that erstwhile folk theorem. But in any case, I'm just going to take it for most of the talk that it is freely generated. And the other salient feature of the superconformal case is the U1R symmetry of the n equals 2 superconformal algebra is spontaneously broken on the Coulomb branch, which gives this Hitchin base a C star grading. So combining these two statements, as a complex variety, the Coulomb branch is a graded vector space with a complicated special Kähler metric on it. Now, you can also talk about the relevant deformations of the superconformal theory. And here, what we do is we relax the condition that the residues of phi are nilpotent. Instead, we say that they should lie on a sheet which contains the nilpotent orbit. The theory of sheets seems not to be as well, as widely known as the theory of nilpotent orbits. So let me just briefly say what they are. If you take the union of all equidimensional adjoint orbits in the Lie algebra, the irreducible components of that union are called sheets. And in SLN, there's a unique sheet attached to each nilpotent orbit. So there's a unique set of mass-deformed theories that you get as relevant deformations of this superconformal theory. But in other Lie algebras, in particular the type D and type E Lie algebras, there can be multiple sheets attached to a given nilpotent orbit. And so there are distinct incompatible ways of mass deforming the theory. You can deform onto this sheet or onto that sheet, and these are distinct deformations of the same the meromorphic Hitchin system. And what we will find towards the end of our discussion is that the set of sheets attached to a given nilpotent orbit, which describes the residue of the pole of phi, is isomorphic to the set of dual non-nilpotent orbits. There's something in the chat. Is it possible?
Yeah, do you see that? John Huerta is asking. Yeah.
I think they're just nicely disjoint, but I'm far from an expert. What will be really important for us today is that typically the superconformal field theories one gets by this procedure are not isolated superconformal field theories, but possess exactly marginal deformations, and so form some kind of family of superconformal field theories, which in this class S context, the family is parametrized by the moduli space of complex structures on this punctured curve. So now I can sort of formulate where we're headed, and one can sort of view what I'm about to say for the rest of the hour in two potentially different ways. For mathematicians, I'm going to sort of construct for you a family of Hitchin systems parameterized by the moduli space of complex structures for a punctured curve. This seems a totally natural thing to do in the context of in the mathematical context. I mean, why not? Sorry, the space of sheets, of course, is a finite set. I think John was asking what each sheet looks like. Indeed, it's a finite set. Where was I? Yes. So I'm going to construct for you a family of Hitchin systems rather than looking at the Hitchin system on a fixed curve. And you can ask what happens when the curve degenerates to a nodal curve. And physics will provide a kind of natural suggestion for what you should do in the case of nodal curves. You'll get a Poisson Hitchin system, which arises very naturally from taking the limit of this family of Hitchin systems over the space of smooth curves. For the physicists, of course, we think of M bar Gn as the conformal manifold, and we'll get a family of Coulomb branches fibered over this conformal manifold. That's not particularly surprising, but what may be surprising is that it's a non-trivial fibration. And you can think of that non-triviality as a new property of the family, not of an individual superconformal field theory, but of the whole family of superconformal field theories. And so what the physicists would like to know is how do you calculate that non-triviality, and what does it mean? So to fix ideas, let me discuss a simple example, which will recur. Namely, take SUN n equals 2 supersymmetric super-Yang males coupled to 2n hypermultiplets in the fundamental representation. That's a superconformal field theory, and it has a one-dimensional conformal manifold, which, as we will see, can be thought of as the moduli space of 4 punctured spheres, which, whose compactification is just CP1, and the boundary points will label conventionally as the point 0, 1, and infinity, and lambda is the coordinate on M04 bar. This weakly coupled Lagrangian description occurs at 2 different points on this conformal manifold, namely at lambda equals 0 and lambda equals infinity. But of course, the degrees of freedom, which are weakly coupled near lambda equals 0, are very, very different from the degrees of freedom that are weakly coupled near lambda equals infinity. Nevertheless, we'll have a whole family of theories parameterized by lambda, and the Coulomb branch for each fixed value of lambda is some n-1 dimensional complex vector space with some complicated special Cayley metric on it. And they fit together to form a rank n-1 holomorphic vector bundle over M04 bar. The transition functions of that vector bundle are what tell you how to relate the coordinates on the Coulomb branch, which are appropriate to the weakly coupled description near lambda equals 0, to those which are appropriate to the weakly coupled description near lambda equals infinity. So this is a perfectly reasonable thing to ask about the theory. How should you relate our description of the Coulomb branch from this one Lagrangian description, good near lambda equals 0, to the other Lagrangian description, good near lambda equals infinity? That's what the transition functions for this vector bundle are supposed to be telling you. Now, I suppose if you stared at Seiberg and Witten's second paper from 1994 long enough, you'd be able to work out the answer, but I will attempt to tell it to you anyways. So first, let's start with Higgs bundles on a fixed curve C. Conventionally, you think of these as the Higgs field as being holomorphic 1-0 forms, which are adjoint valued, and because we're interested in marked points, we'll allow poles with nilpotent residues at the punctures. And so if T is some local coordinate near one of the punctures, phi locally will look like some nilpotent divided by T plus regular terms. If your collaborator is an algebraic geometer, you quickly learn that a better description is one where you twist the canonical bundle of the curve by the divisor consisting of the sum of the points. And now we think of phi as being this same nilpotent x plus terms that vanish as you approach the point t equals 0. The reason why this is convenient is that in this description, the spectral curve, excuse me, the spectral curve we're about to write down is a compact curve as opposed to this one where it's non-compact. So here's the spectral curve. It's the zeros of the characteristic polynomial. And for type A, it takes the following form. And for type D, the odd powers of W, the fiber coordinate, are absent. There are only even powers. And the 0th order term is actually a square of something called the Pfaffian. So the phis are holomorphic sections of certain line bundles, which are the kth tensor power of the twisted canonical bundle of the curve. But then we demand that these sections vanish to certain orders at the marked points. The PA are the marked points. There are little n of them. So at each marked point, we'll have a nilpotent element of the Lie algebra, and the nilpotents in the classical Lie algebras are labeled by partitions. And I can tell you the 0 orders in terms of the data of this partition as follows. Let's let K sub j be the partial sums of all of the parts up to j. And then chi sub k is the value of j such that k lies between k sub j minus 1 and k sub j. So upshot is, in local coordinates, these little phis, which are gauge invariant, are vanished to order chi sub k at the marked point. And then the leading coefficient, who will be the hero of our story, are the c sub k's, which are polynomials on the Lie algebra. And I'll throw in a condition which will be implicit in everything I'm going to say going forward, namely, for genus 0, then I have to choose these collection of nilpotents XA such that the higher cohomology of this line bundle vanishes. It's just some condition or other. Okay, so now having worked things out for a fixed curve, I can now globalize and write the whole thing for a family of curves. So we have the universal curve over MGN bar, and these line bundles L sub k over a fixed curve C fit together to form some line bundles curly L sub k over the universal curve. Before we were supposed to take holomorphic sections. Now the thing what we want to do is take the direct image sheaf of these curly L sub k's. So pi was the projection from the universal curve to the moduli space. Pi lower star is the direct image. And for full punctures, namely the XA being the regular nilpotent orbit, that's the whole story. The Hitchin base is a vector bundle, is a graded vector bundle over the moduli space MGN bar, and the graded components are just the direct images of these L sub k's. So as an example, let's take the 4-punctured sphere. So the moduli space of the 4-punctured sphere, as previously mentioned, is just CP1, and the universal curve is a complex surface known as del Pezzo 4. for four full punctures, so again, the XAs are the regular nilpotent in SLN, then all of the chi's for each of the points and every value of k are just equal to 1. In other words, we demand that everything vanish to first order at the marked points. The rank of this graded piece of this vector bundle of Hitchin bases is 2k minus 3, but we know more than that. It's every vector bundle over the Riemann sphere splits as a direct sum of line bundles, and this vector bundle B sub k splits as follows, depending on whether k is even or odd. It splits as a direct sum of line bundles of varying degrees from 1 on up to L, where k is 2L or 2L plus 1, as the case may be, with these precise multiplicities. So let me, in order to give you some sort of more concrete picture of things, let me just say some words about the construction of this universal curve. So Del Pezzo 4 is CP2 blown up at 4 points. And so I have exceptional divisors E1 through E4, and I can take those as the blowups of these 4 points in CP2. And then the projection from the universal curve to the moduli space is given by some equation that looks like this, where lambda, the coordinate on M04 bar, is just the ratio of the homogeneous coordinates lambda 1 and lambda 2. And for a generic value of lambda, the fiber is just a smooth quadric. But for lambda equals 0, 1, or infinity, it degenerates to a pair of lines meeting at a node. So I should have said I've written this equation as a map from CP2 to M04 bar, but it actually extends over the exceptional divisors. You can, with a little bit of work, see that it extends over the exceptional divisors and is actually a map from Del Pezzo 4 to M04 bar. So that was the story with full punctures. The story with when the punctures aren't the full punctures, then when they're not the regular nilpotent orbit, then things get slightly more complicated because the direct image of the L sub k's can fail to be locally free when the curve degenerates. The rank of the stock can jump. But the physicists know what to do, because when the curve degenerates, that's weak coupling. And if there's anything physicists know, it's how to handle weak coupling. What happens when the curve degenerates to a union of curves intersecting at a node is that the conformal field theory breaks up into a conformal field theory associated to C left, a conformal field theory associated to C right, and if we're not quite at the node in the nodal limit, then it's weakly gauged with some weak gauge coupling in some subgroup of some diagonal subgroup of the flavor symmetry of the two conformal field theories. And the issue that I'm talking about here can be summarized as follows: when C left has genus 0, and if the collection of points, of the marked points that land on C left when the curve C degenerates, are sort of in sufficiently low dimensional nilpotent orbits, then what can happen is that CFT right is a class S theory with the puncture at what the erstwhile node, which is not in the regular nilpotent orbit. It's in some other nilpotent orbit. And then what we have to do is we replace the line bundle curly L by something twisted by some power of this component of the boundary divisor, C left. I'm using curly C instead of Roman C, just to indicate that it's a divisor sitting inside of the universal curve corresponding to this component of the boundary curve. And then the bundle of Hitchin bases is the direct image not of L, but of L prime. So back to our, yes?
Let me have a question. I have a question about this. So could you go back?
Sure.
Are you, no, the glowing condition. So it seems that you're saying that the residue XA has to be in a sufficiently low dimensional nilpotent orbit. Are you saying it has, there are conditions on the XA in order for this glowing formula to be true?
So for an arbitrary set of XAs, so there was a condition on the XAs, at least when C itself had genus 0, which was that okay condition that the higher cohomology vanish?
Mm-hmm.
Okay. Well, now when C degenerates and one of the components has genus 0, you have to revisit that okay condition.
Mm-hmm.
And that's essentially what's going on. What happens over here is that on the, we've guaranteed that there was no higher cohomology on the smooth curve, right? But when the curve degenerates, you can develop an H1, and compensatingly H0 also jumps.
Let me see if I understand. So C left, you say, is genus 0. So it's trying to be a class S theory for genus 0 with one puncture?
It could be 2 punctures or 3 punctures or whatever.
Ah, okay. So
some number of punctures end up on this genus 0 component of the
but still you're saying
generating curve.
I'm trying to understand. So you're saying it isn't factorizing with the regular orbit in general.
Right.
How do we decide what it does factorize on?
Well,
bottom of the page?
I'll try to tell you that.
Okay.
Okay. So let me yeah. So in general, it will we'll have to twist by this C left to get something that for which the higher cohomology on the nodal curve vanishes. That's the condition. So let's do our SUN with 2n flavors example, and we'll have simple punctures, namely the minimal nilpotent orbit at P1 and P2, and the full puncture, or the regular nilpotent orbit, at P3 and P4. So my L sub k is the kth tensor power of this twisted canonical bundle. And then I have simple zeros at P3 and P4, and zeros of order k minus 1 at P1 and P2. When you degenerate this 4-punctured sphere in such a way that P1 and P2 end up on one component, and P3 and P4 end up on the other component, you land yourself in this unfortunate situation that Greg was just asking about. And the solution is to twist L by a multiple of the component on which the simple punctures landed, namely C12. And when so the answer to your question, Greg, is that this thing is sewn with the partition, which is the hook partition. It's got one column. It's got it's whatever it is. It's the subregular orbit rather than
okay.
Okay. Yeah. Sorry.
Is it the orbit or a orbit? Because it's not the
No,
same.
actually, sorry. It's not the same. It's a hook partition, but it's the hook partition. I think it's 3, 1 to the n minus 3.
No, I'm just saying it doesn't need to be nilpotent anymore, does it?
Oh, no. So the if I go back to this picture, right? The theory near the nodal limit is some weakly gauged version of CFT left cross CFT right. And CFT right is the theory on a 3 punctured sphere with two regular nilpotents and one nilpotent given by the aforementioned hook partition. And H here is SU2. Okay? Whoops, I didn't finish. So anyways, if you now take the direct image of this L prime, what you find is that B sub k, which is rank 1 for every value of k, is just the hyperplane bundle O of 1. And this tells you now how to relate the Coulomb branch parameters to the weakly coupled Lagrangian field theory near lambda, the Lagrangian field theory that's weakly coupled near lambda equals 0 to the Lagrangian field theory that's weakly coupled near lambda equals infinity. It's governed by the transition functions of O of 1. And so you can write down a bundle of spectral curves. Well, you have to write it down in some trivialization. There's one trivialization which is good in the northern hemisphere, a different trivialization which is good in the southern hemisphere, and then the Coulomb branch parameters are related by by these transition functions, as you'd expect. So that's
sorry, Jacques, I have another question. I mean, these theories have S duality, right? Is lambda equals 0 and lambda equals infinity related by tau goes to -1 over tau?
Lambda goes to 1 over lambda. Yeah.
Okay.
But the Coulomb branch parameters that are the things built out of, traces of fundamental fields in the Lagrangian description are different because the field theories are different, right? I'm telling you actually how they're related. They're related by the transition functions for this bundle.
Right, I'm getting that, but I just wanted to make sure that these are the two weakly coupled regions related by S duality. Is that correct?
Right.
Okay.
So the more general story, that was a 4 punctured sphere, but we can actually write down a formula in general, is you have a collection of n points, and you can study what happens when the surface degenerates so that any subset of them containing at least 2 of the points lands on one side of the pinch of the node, and the rest remains on the other side. And if I'm going to be really pedantic, if the curve had genus 0, then the complement also had to have at least 2 points. And then let curly C sub S be the component of the boundary divisor corresponding to a genus 0 component of C with this collection of marked points labeled by this subset S landing on that component of the nodal curve. Then what we're supposed to do is twist by some multiple of C sub S summed over all such subsets. You twist by this multiple of the corresponding component of the boundary divisor, where these integers are given by this expression over here. And rather perversely, I've thrown in what the formula would be if this component C sub S had genus bigger than 0. But you can, and I threw that in only to show you that you might as well restrict yourself to genus 0, because if G is bigger than 0, then the max here is always 0, and you're not twisting by that component. So we might as well restrict our sum to genus 0, to degenerations of the curve where one of the components has genus 0. Okay, so that was all type A, and maybe I should pause for a bit and ask whether there are any questions about type A. Any more questions about type A? Okay, so on to type D. Nilpotent orbits in SO2N are labeled by what are called D partitions. And these are partitions of 2N where even parts occur with even multiplicity. What crops up in physics, that's to say the Hitchin systems that we end up studying in class S, are not the residue of the Higgs field is not just any old D partition, not just any old not just a nilpotent orbit labeled by any old D partition, but rather only special D partitions, where there are an even number of odd parts between any even parts, including at the beginning and the end. You'll see a number of features of what I'm about to say, which will depend crucially on the fact that the D partition was special and not just an arbitrary D partition. So in any case, I've repeated what the characteristic polynomial looks like, and the spectral curve will be the zeros of this polynomial, where the phi 2k's again will vanish to some order given by these chi's at each of the marked points, and phi tilde is, as I said, the Pfaffian, which is I can think of this as the square root of phi sub 2n. Now, by construction, so what I want to do first is study just the local story near one of these marked points. And so I'm going to really be studying this kind of expression for a little bit. By construction, these coefficients C2k are polynomials in the coefficients of this G that was an element of the Lie algebra. The surprising thing is that unlike in type A, these leading coefficients are not all independent. Instead, they obey polynomial relations. So there's an obvious one, namely, if I look at C2n, which is the leading coefficient in this term in the characteristic polynomial, it's the square of the leading coefficient in phi tilde. So that's actually familiar. But the amazing thing is that there are additional, depending on what nilpotent orbit we choose, there can be additional polynomial relations on the C's. These were discovered much to, excuse me, my displeasure by my student at the time, Oscar Chakaltana, and I, back in 2011. And they were rediscovered years later by Baralia and Kamgarpur in the mathematics literature in this paper over here. In a slightly restricted context compared to what Oscar and I found, but with a much clearer understanding of what was going on. So the polynomial relations that you find come in two types, which I call even type constraints and odd type constraints. So I'm first going to describe the even type constraints. So for every even part of P, remember the even parts have to occur with even multiplicity. So let's say this partition P looks like something, the ... some part 2s raised to with multiplicity 2l. In other words, P sub 2j plus 1 through P sub 2 times j plus l is equal to 2s. Let K again be the partial sum of all of the parts of P before this even part. So this ... over here. Excuse me, half of that. Here again, I've used the fact that this partition was special because that sum is even. It wouldn't be even if the part weren't special. But anyways, here it's even, so we can divide by 2. And then the claim is that there's a polynomial relation of the form, just introduce some formal parameter u and write down a polynomial of degree 2L in u, whose coefficients are C2k, C2k plus S, on up through C2k plus 2L plus S. And the statement is that polynomial is a perfect square. You'll notice that there are many fewer coefficients on this side of the equation than there were on the left-hand side. And therefore, there are relations among the coefficients. Remember, these are the C's that we were interested in. There are relations among the C's which are given by the fact that this polynomial is a perfect square. And that was essentially what Oscar and I discovered way back when. And we found, although it was, again, really only experimental, that the A's are also polynomials on the Lie algebra in the same way that the C's were, gauge invariant polynomials on the Lie algebra in the same way that the C's were. And so they are good candidates, better candidates for parametrizing your Hitchin base. Why not use these gauge invariant polynomials instead of those ones? So in our paper over here, there was actually a slight gap in the proof. We didn't prove that the A's were, in fact, polynomials in all of the cases we needed. That gap in the proof was recently filled by Ron's son Nathan. And the theorem that will appear sometime soon is that whenever P sub 2j, the 2jth part of this partition, is greater than P sub 2j plus 1, then the corresponding C sub 2k is actually the square of a polynomial on the Lie algebra. It's not just a polynomial. It's not just it itself as a polynomial, but it's actually the square of a polynomial. And with that, we were able to prove that in many cases, but not all of the ones we needed. But with that, this really becomes a hard theorem that you should use the A's rather than the C's as the coordinates on your Hitchin base. And in some cases, well, for instance, let's say your even part occurs at the beginning of the partition, then you use the fact that C naught is defined to be 1, and as is A naught, and then you can successively solve for the A's in terms of the C's and plug back in, and what you find is just that some of the C's are redundant. They're determined as polynomials in the lower order ones. And so you're again just using C's as your coordinates on the Hitchin base. But more generally, when you're not at the beginning of the partition, if you're just at some random location in the partition and you have an even part, you can't solve for the A's in terms of the C's. The A's are the non-redundant parameters, and we should really, if we're being sensible, use them as the parameters to parameterize the Hitchin base rather than the C's. There's another set of constraints, which is slightly more subtle. They're the ones that we called odd type constraints. And so remember, this theorem says that whenever this part is bigger than that part, then the corresponding C is a perfect square. We use that in here when this was an even part, but we didn't have to. We could just have a situation where these are two odd numbers, and it happens that this odd number is bigger than that odd number. So then you have that this coefficient is a perfect square, and you should ask yourself, should you use A sub k or C sub 2k to parameterize the Hitchin base? And what I want to claim is that it's actually a choice. If there are S such pairs in your partition, then there are 2 to the S possible choices, depending on whether you use A or C for each such pair. And so there's a whole set of different possible Hitchin bases, which are related by some kind of double cover operation. C is equal to A squared. And the statement is that there are, which we do prove in the paper, is that there are bijections between 3 sets of 2 to the S elements. So I just described these 2 to the S choices of local Hitchin base, whether you use C sub 2k or A sub k. And then you'll recall way back 45 minutes ago, I mentioned that there were 2 to the S sheets attached to this nilpotent orbit. Well, I didn't tell you the number. Now I'm telling you the number. There are actually 2 to the S sheets attached to this nilpotent orbit. And there's a 1-to-1 correspondence between which choice you make here and a choice of sheet over here. And moreover, the 2 to the S sheets are in 1-to-1 correspondence with 2 to the S non-nilpotent orbits in the special piece. So what do I mean by that? So there's this partial ordering on the set of nilpotent orbits given by orbit closure. And there's an order reversing map on the set of nilpotent orbits called the Spaltenstein-Barbash-Vogel map. And its image is the set of special nilpotent orbits. And on the special nilpotent orbits, it's a bijection. So on a special nilpotent orbit, D, let's call this map D. D squared is the identity. But it has a kernel and it has a co-kernel. And all we have is that D cubed is equal to D on an arbitrary orbit. So if I ask, given my Hitchin nilpotent orbit, which, as I said, had to be special, its pre-image under this map D, there are 2 to the S orbits which map to the same special orbit, X, I called it. And a choice of non-nilpotent orbit over here, of course, is in 1-to-1 correspondence with a choice of sheet attached to this nilpotent orbit, and the choice of Hitchin base determines which sheet we're allowed to mass deform onto. So if you want a good family of mass deformed spectral curves, you have to make a choice, and there are various choices which pick out which sheet you're allowed to deform onto to get a nice family of mass deformed spectral curves. Questions?
Is that sheet related to some topological coupling?
No, these are just
Excuse me,
where the masses live.
You have these choices of mass deformation.
Right.
Are they somehow related to adding a topological coupling to the Lagrangian?
No. So on the norm side,
So more physically, what are these choices?
physically, the SCFTs have different flavor symmetries, and the mass deformations correspond to turning on, moment maps in the flavor symmetry algebra, the Cartan of the flavor symmetry algebra. And so the flavor symmetry,
different choices of which masses you're turning on. Is that
right? Well,
okay.
Mutually exclusive choices is the point.
Mutually exclusive.
Yeah. So let me give you an example. Let's take the partition 3 squared 1 squared. Okay.
Okay.
That's special because there are there are no even parts, so that's special. Its pre-image consists of 2 orbits, 3 squared 1 squared and 3 2 squared 1.
Okay.
So one of those is special, namely 3 squared 1 squared. The other one, 3 2 squared 1, is non-special. But they both map to the same Hitchin nilpotent.
Okay.
So, and they have different flavor symmetries. If you sort of construct a class S theory with one or the other, you get for 3 squared 1 squared, you get a U1 squared flavor symmetry. And for 3 2 squared 1, you get an SU2 flavor symmetry.
Okay.
So in the first case, I would say I have 2 mass parameters that I can turn on. They're Cartan of U1 cross U1.
Okay, that's clarifying. Okay.
And in the second case, I can only turn on just the one, right? The Cartan of the SU2, right? And so what I'm saying is that attached to 3 squared 1 squared are 2 sheets, one of which corresponds to the first norm orbit and the other one of which corresponds to the other norm orbit.
Two sheets, but also, do I understand right? It's just 2 different SCFTs.
The 2 different SCFTs, I was trying to describe everything in terms of Hitchin data, right? And so the relevant deformations of these are 2 completely different SCFTs, but whose Hitchin data in the conformal limit looks identical.
Got it.
Right? And what distinguishes them is what the allowed set of mass deformations are. Right? One of them has a 2-dimensional space of mass deformations onto one of the sheets attached to this nilpotent. The other one has a 1-dimensional space of mass deformations corresponding to moving onto the other sheet attached to this nilpotent. Okay, so that I think is hopefully clarifying. So I'd like to now sort of say where we're headed and talk about some of the issues that crop up. So so far I've just told you about the local story in type D. We also have a global story, fitting these things together into families. And I would say we understand 90% of what needs to be done, but there's still a few picky issues that arise in type D that didn't arise in type A that are still slightly confusing. There's also the local story in type E, which, as far as I can tell, there's zero mathematical literature which understands the constraints there. And part of the difficulty is that whereas the story I told you for type D just involved these leading coefficients of the phi's as I approach the marked point, the leading order terms as t goes to 0, the constraints in type E involve a whole mess of subleading coefficients as well. And so you can work it out by hand. Oscar and I worked out E6 and E7, and half of E8. E8 has 69 non-zero nilpotent orbits, and I think we worked out what the constraints are for 35 of them. But we never wrote that up because well, doesn't make sense to write up half the story. But it's really just formidable to try to do by hand. So I really wish there was a theory behind it. But what I'd like to do, I'd like to end with is kind of a question about non-freely generated Coulomb branches from these even type constraints. So let me go back to that story, right? So we had these polynomial relations, right? And what I told you was, oh, we should just treat the A's as our Coulomb branch parameters, not the C's. The C's obey complicated polynomial relations. The A's are just to freely generate the Coulomb branch chiral ring, and so we should go with with them as our generators, not the C's. And then on the next slide, I said, oh, but for odd type constraints, I have a choice. I can use A or C. And so you might say, well, why not? Oops. Why don't I have a choice here? Maybe I could use the C's instead of the A's. There's a disadvantage, of course, because if I use the C's instead of the A's, then the chiral ring has relations, as we just said. It's some complicated singular complex variety, still with a C star action on it, but it's complicated, but definitely not freely generated. And in some instances, I can actually write out sensible looking families of Hitchin systems, whose base is that non-freely generated complex variety. But I don't know whether that's sort of true in general, or whether that's just an accident of, some low dimensional examples that I sort of know the answer to. But if it were possible to construct a Hitchin system with the C's as the Hitchin base in general, you would have a huge, rich set of examples of non-freely generated Coulomb branches. There are a dime a dozen. Whenever you have an even part in this partition, you would get such a thing. And so they'd be ubiquitous in the Hitchin systems associated to class S theories of type D and E. Most of your Coulomb branches would have non-freely generated chiral rings. So I hold that up as an interesting possibility to think about for future work. I don't know whether it's true or not. It's just speculation, but it's the end of the semester, so why not speculate? And with that, I will end.
Thank you very much, Jacques, for the beautiful talk. Questions? I think all the people who have been applauding are also muted.
Well, I have a question, but I've asked a lot, so
Well, please.
I'll wait for
Go
other
ahead.
people. Well, I guess I have two questions, actually. One is that at various points when you were pinching the curve into two, you had various conditions in order to get good results.
Mm-hmm.
I'm wondering if those conditions are related to the physical condition that if you try and define a class S theory from 6 dimensions, then you want to be able to take, let's say that it's a genus 0 curve you've pinched off with punctures. You want to be able to take the area to 0.
It's very much related to your paper on that.
Okay.
So
I
let's
didn't recognize that. I just recognized that in that situation there were conditions.
right.
So
Well, let's go back to your favorite example.
Yeah.
Right. So the issue arises when I take the two minimal nilpotent orbits,
Right.
put them on one side of the pinch.
Right.
Right.
Yeah.
And as I said, the way I should think of the SCFT on the other side of the pinch when I turn off the gauge coupling, right, is two regular nilpotent orbits plus the hook partition, which is
Right.
1 to the n minus 3.
Right.
Right.
Yes.
So I mean that's exactly when I get this twisting.
Okay. All right. I'd like to understand the relationship between the two stories. I see that they're discussing the same puzzle, but I don't quite do.
Well, actually, to be really honest, there are two parts to the story. So which I should have probably interjected a slide about. So what I would like to say, if I go back one more slide, what I would like to say is that on CFT right, I should really think about a pair, namely the nilpotent that I stick at the erstwhile node,
Yeah.
and a subgroup H of its flavor symmetry that I'm going to gauge.
Right.
Okay. So I could stick the full puncture, I mean the regular nilpotent at the node, and gauge the full flavor symmetry group. That's what I'll call a standard puncture. Okay. But I could also have the full puncture and gauge only a subgroup.
Right.
Right. Or I could have some not full puncture, some, you know, not orbit that's not the regular orbit. Right. So I would say you have a story to tell about taking the area goes to zero limit. Any case, it's not the standard node. Any case where it's not the full puncture with the full flavor symmetry group.
Okay.
Here, there's no, if it's the full puncture, there's no twisting. Only if it's not the full puncture do you have to twist.
Okay.
Okay, so there's an intermediate case, namely full puncture and subgroup, you know, proper subgroup H of G, that the area goes to zero limit is slightly funky, but it doesn't involve this twisting.
Okay. All right, well, that helps. Maybe I'll ask my other question. I'm wondering if there's an application to the following question of your global picture of these class S theories, global on the conformal manifold. So, you know, it's interesting to think about the coupling of the Seiberg-Witten Lagrangian to gravity. Right, so they're the A and B coefficients related to the little a and little c anomaly coefficients. And so so capital A is the coupling to the Euler density, and capital B is the coupling to the signature density in the effective Lagrangian in the presence of curved metric. Now, as a function on the Coulomb branch, we know capital A and capital B up to an overall scaling, which could in principle be a function on the conformal manifold, or maybe a section of a bundle on the conformal. And I've wondered for a long time in some examples that those coefficients, let's call them alpha and beta, I think should be interesting Teichmuller modular forms.
Oh, that's interesting.
And their zeros, maybe poles. Well, I mean, there are examples that I've worked out with Jan Manscott and Xinyu Zhang where we know that's true, but they're simple examples. And I think there should be a story for general class S. And I think what would you need to figure out what amorphic forms those were? I mean, you'd have to figure out what line bundles they're sections of over the compactified conformal manifold, the M bar G.
Right. So I mean, in general,
I don't know. I mean, since you're extending the whole Hitchin system over there, I'm wondering if in principle one could even figure out what these Teichmuller modular forms, or at least where they live, what sections of line bundle they are.
Does the answer for N04 bar give a first hint? Or is that too simple?
Well, for n equals 2 star, you know, they're related to powers of the eta function. Right. So the way I would put it is for n equals 2 star, let's just take SU2 n equals 2 star. But that's one of your examples, right? I think of these things, I think, you know, I go up to Teichmuller space. So I think of these coefficients, alpha and beta, as functions of tau.
So for Ron's benefit, n equals 2 star is the once punctured torus.
That's correct.
Thank you.
That's correct. So So we're studying things as a function of the modular parameter of that torus.
Mm-hmm. Mm-hmm.
And in that case, we found it by instanton, Shenju Zhang is a great expert on these instanton partition functions. So we got it from the instanton partition function, and with Jan, we got it in a different way. So anyway, it's some power of the eta function.
Mm-hmm.
It shows that in general, it's non-trivial.
Yep.
But there ought to be some general story in terms of typolar modular forms that one could tell. But in order to be able to tell that story, you would have to be able to extend. I think you'd have to be able to, yeah. So let me, okay, now I see a more efficient way to ask my question. So you told us the low energy effective action over, well, we know the low energy effective action over the conformal manifold.
Mm-hmm.
But now let me ask you, what is the low energy effective action in the presence of a curved metric? So we know we have to add a function times the Euler density and another function times the signature density.
Mm-hmm.
Now from hocus pocus, we know what they are as functions along the Coulomb branch for fixed point in the conformal manifold, but they can scale with if I think multiplicatively, capital A to the chi, capital B to the sigma, that capital A and capital B are only determined up to a function locally a function on the conformal manifold, more likely a section of a line bundle.
Mm-hmm.
So I think it would be interesting to, possibly to, apply what you're saying to figure out what that would be. Because, figuring out that line bundle is just going to have to do with figuring out R symmetry anomalies. And so maybe I could ask, do you really understand the R symmetry anomalies at the boundaries of MGN?
Yeah. Well, again, going to the boundaries a little bit tricky because the Hitchin system sort of degenerates, right?
Yes.
So we need to think carefully about what that. The thing I told you is the thing that's sort of robustly understood in that limit. I need to wonder a little bit whether those coefficients capital A and capital B are also robustly understood in that weak coupling limit.
Well, you Jacques, in your papers, you studied the little a and the little c, right?
Right, sure. Well, those are just constants.
But they don't jump or anything on the.
No, those are just constants, right?
Okay,
so they don't jump.
That's good. Okay.
Right.
That's good. Okay. Well.
Okay. That's it. Well, certainly that sounds like an interesting thing to think about.
Other questions? Okay, so let's thank Jacques again for the beautiful talk. And we'll see you all in the fall.
Excellent.